Okay, so we're going to start part two of the astrophysics course with the topic of stellar characteristics and evolution. We're going to look at stellar spectra, which is the light that comes from stars and what we do with it. And this is part one of this because it's quite a big topic. Okay, so that's where it falls in within the overall list of what we're doing. And here are our learning objectives. We're just going to be understanding stellar spectra, and in this first part we're going to be explaining how surface temperature can be obtained from a star spectrum, and the data book equation of relevance is down there. Now, if you handed me this diagram as part of a lab report, I would probably not be very happy, but this is actually from the original notes of Sir Isaac Newton from his experimental notebook, recording his experiments in 1666, where he took light from a chink in the window, cut in the curtains, focused it, and then dispersed it using a prism, either to display a series of colours or to recombine it back into white light again. And here's a depiction of the same event. So he was the first person to scientifically investigate the continuous spectrum, which he did by looking at sunlight. Of course, humans have been seeing a continuous spectrum of colours since there have been humans, because that's what a rainbow is. Instead of a prism, it uses raindrops and total internal reflection, but the basic principle is the same. This is sunlight being split into its component wavelengths, and this is the full range of a visible spectrum, from short wavelength blue through to long wavelength red. Diagrammatically, a hot black body, we've been introduced to the concept of black body earlier in the course, is dispersed, forms the continuous spectrum between about 400 nanometers to 750 nanometers. If we plot a curve of the radiation output, then we'll see that it depends on the temperature. By our eyes, we can't really tell you that there's more or less white or yellow or green or blue or red. But if we use a photometer to actually measure the different wavelengths of light in these filters, then the peak output is somewhere actually around in the sort of greenish area. And the description of what was happening was first realized really by Planck, working in Germany in the late 19th century. And he derived this equation, which is one of the foundational equations of atomic and quantum physics. But we apply it here, and it's almost surprising, but probably isn't surprising, how much of an overlap there is between quantum physics, the physics of the very, very small, and astrophysics, which we tend to think of as the physics of a very, very large. Well, that's not strictly speaking true. Astrophysics covers all scales. Anyway, what this equation, which you do not need to know, describes is this curve, which you do need to know. It says that the wavelength output per nanometer per meter squared, because obviously the total output depends on the size of the object, its surface area, but the output per nanometer of wavelength depends on the temperature of the object. Everything in the universe emits radiation, electromagnetic radiation. For most cool things, this is deep into the infrared, into the radio, microwave, etc. But for objects above about 3,000–4,000 Kelvin, a very significant part of it is in the visible. The peak moves and moves and moves until you get to above 7,000 Kelvin. The peak actually moves into the ultraviolet part of the spectrum. You do not need to know this equation. You do need to recognize that shape, and you do need to know that there is an equation which connects where this peak wavelength is found to the temperature of the object, and that is known as Wien's displacement law. And again, you've met this before, you should be familiar with it by now, but here is its in its application. So lambda max T equals a constant, 2.9 times 10 to the minus 3 meter Kelvin. Rearrange that, and you have the equation from which you can find the temperature if you know the maximum wavelength. For example, a maximum wavelength of just over 400 nanometers, you should be able to go through that and work out, and it will give you 7,000 Kelvin. Let's put that into practice and demonstrate a real example. Let me introduce you to my little friend, SDSS J11210 0.85 minus 0.1111 5.1. that very ordinary looking star there. It's not a very ordinary star, it's actually quite an unusual star. It is a little star. This is the Sloan Digital Sky Survey, SDSS, and that's a bit of objects. It's basically a robotic telescope which just takes pictures of the night sky. And then we can go back and mine the data to do scientific research, rather than getting a telescope ourselves and specifically pointing it at a part of the sky. It's a much more efficient process. And not for every object, but for several of them, they record the spectrum, and this is what ours looks like. You'll see that the units are angstroms for wavelength, because astronomers. An angstrom is 10 to the minus 10 meters. We won't even look at the units there, that's just way too bad. But the basic shape of the continuous spectrum, the Planck curve, should be obvious. You will notice there are certain dips, and you may even notice some chemical element names, but we'll explain that shortly. And you'll notice that it has a defined peak, and we can find out where that peak is. We can identify the wavelength, we can plug it into Wien's displacement law, and we can find a temperature for that object. Another example, very similar. Here's another SDSS plate. Nice galaxy there at the center. There's another little star. There's further information about its brightness and its location. And here is the stellar output. Many of the lines are in the same place, which we'll come back to later, but the peak has shifted. It still has that characteristic shape, steep on one side, curved down on the other. But again, we can find out what the temperature is from the wavelength there. You can do this project yourself using the web access to the Sloan Digital Sky Survey. This is, as I said, a very professional and used by professional astronomers and astrophysicists and researchers, but you have all the same access to the data that they have, and you too could investigate different stars. One challenge you may find is that, as I kind of indicated from the earlier graph, if a star has a surface temperature way less than 3000 Kelvin, which is unusual, but some do, then you'll find the peak is deep into the infrared, and you won't be able to see it. These spectra do cover the near infrared, but not the far infrared. And a very, very hot star, conversely, in the other direction, will go over to the ultraviolet. And this detector on this telescope is an optical detector, so it can only detect that wavelength range. Professional astronomers would actually look at a spectrum, and rather than find the peak wavelength, they'll just pull up on their computer a big database of previously observed and measured spectra, and they just find one that looks similar. And from that one that looks similar, they will know the information about the star. Okay, that's the end of part one. Coming back in part two for more information from a star's spectrum.